Hello everybody. So this video is going to take a look at conditional probability. So what conditional probability is, it is the probability of an event occurring given that another event has already occurred. So there is this formula here, and you can see depending on what version of the book you have, I've made some edits to it because it printed incorrectly. But we have these formulas, these variations of the same formula. The first one says the probability of A and B happening is equal to the probability of A times the probability of B, and then there's a line and then A. And what this means is it is the probability that event B will happen given that event A has already happened. We can also rearrange this formula to solve for the conditional probability. That's what this given thing means. This is our conditional probability. Okay, we can solve for that by saying that is equal to the probability of A and B divided by the probability of A. So just make sure that you are making these edits in your book if you do not have one of the edited versions of the book. Okay, now what we're going to do is we're going to take a look at what this looks like through a number of examples. So example number 1 says a manufacturer knows that in a box that has 100 computer chips, 3 of them are going to be defective. Then Joy is going to draw 2 chips at random. So she's just going to reach into the box, pull out a chip. Reach into the box, pull out another chip. What is the probability that both of the chips will be defective? So what we are calculating here is we are calculating the probability that chip 2, the second chip, will be defective, and chip 1 will also be defective. I kind of wrote these in the wrong order. I should really do chip 1 and chip 2. Okay, so what is the probability that this chip and this chip will be defective? So we can use this formula here, which is the probability of the first chip being defective times the probability of the second chip being defective, but given that the first chip that we pulled out was already defective. Okay, so that's how we can interpret this problem. Now, you don't necessarily have to write the formulas out like this, but you should at least understand where the probabilities are coming from. Okay, so if we reach into a box, we're just going to randomly pull out a chip. The probability that it is defective is 3 out of 100 because there are 3 that will be defective out of the box of 100. But now the second probability, we're not putting that chip back into the box. So now we've already pulled it out, we're not putting it back in. So that means we have 99 chips left in the box and only 2 of them are defective. So this second probability, it's kind of like thinking back to the previous unit when we are counting down our options. So we have, like, for example, 10 factorial. We have 10 for the first, then 9 for the second, then 8 for the third, and so on and so on and so on. This same kind of counting down idea applies here for conditional probability. So again, we had 3 out of 100. Initially, we pulled one out. We are assuming that it's defective. So what would be left? There would be 99 chips and only 2 of them would be defective. So when you multiply this out, you get 6 over 9900. And you can simplify this fraction if you want. I'll just do it here quickly. The simplified version, I believe, is 1 out of 1650. I could be wrong about that, but this is good enough as your answer. Example number 2 says Matt chooses a number between 1 and 20. The number that Matt chose, he says that it is a multiple of 2. We're going to determine the probability that that number is also a multiple of 9. We're going to do it 2 different ways. One of them will use a Venn diagram. The other one will use just the formula above. Okay, so if we were to draw a Venn diagram, I'm going to say that T is going to be my multiples of 2, and N is going to be my multiples of 9. Okay, so we're going to draw our circles like so. I'll draw it in a box here too. So these will be my multiples of 2, these will be my multiples of 9. So my multiples of 9 are just 9 and 18 if we're considering the numbers between 1 and 20. 9 is not a multiple of 2, but 18 is a multiple of 2. So the 18 is going to go into the middle. And then I can write all my other multiples of 2 just in the T, but they don't go in the middle because they are not also multiples of 9. So I have 2, 4, 6, 8, 10, 12, 14, 16, and 20. We're not including 18 because it is already in the middle of my diagram. And then outside of the Venn diagram are going to be all of my odd numbers. Again, we're not going to write 9 because 9 is already in the Venn diagram. But we can write all of our other options outside of the circles, but still inside of the box, which is our sample space. So what is the probability of getting a number a number that is a multiple of 2 and a multiple of 9? Well, we only have one option for that. So we have one favorable outcome, and we have 20 total numbers. So it's going to be 1 over 20. Now, if we consider the formula way, again, we want to calculate the probability that we have a multiple of 2 and a multiple of 9. Okay, so that's how we would write it using the formula. And how we can interpret it is the probability of getting a multiple of 2 times the probability of getting a multiple of 9, given that we know that our number is a multiple of 2. So the probability of getting a multiple of 2, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 multiples of 2 between 1 and 20 over 20 possible options. Now this is where, again, the probability of the second one, the conditional probability, might look a little bit weird. It is the probability of having a multiple of 9 given that we already know that it's a multiple of 2. So what we're doing is we're looking strictly at the multiple of 2. We know that there are 10 numbers that are multiples of 2, and how many of them are also multiples of 9? There's just the one. So this probability would be 1 out of 10. So when we multiply these two fractions together, whether you just want to multiply straight across, or if you're good at simplifying your fractions before multiplying, I'll just multiply across. So 10 times 1 is 10, 20 times 10 is 200, and if we simplify this, we can just cancel out one of the zeros in each of the numbers, is 1 out of 20. So you can see that whether we drew it out or whether we use the formula, we got the same answer. And there are multiple ways that you can approach it using not even just a formula, but just using math and logical thinking in general. We could also use a tree diagram to do this. So I'll kind of show that off here. So this is my multiples of 2, and this is my not multiples of 2. So we have a 10 out of 20 chance to get a multiple of 2 and a 10 out of 20 chance not to get a multiple of 2. And then beyond this, we also want to consider the multiples of 9 and not multiples of 9. So multiple of 9 and not a multiple of 9. I'm writing it very shorthand, but the chance that we get a multiple of 9 here is 1 out of 10 if we just look at this diagram here, and 9 out of 10 for it not being a multiple of 9. We can also fill in the bottom part of this tree diagram, but it's not going to be important. So what we want to do is we want to calculate the multiples of 2 and the multiples of 9. But again, we have the same fractions just like we did when we used the formula. So it doesn't change our answer in any way. We're just going to multiply those fractions together and we get the same answer. All right, example number 3 says that according to a survey, 91% of Canadians own a cell phone, and of the 91%, 42% of them have a smartphone. I can already see this question is very outdated because I'm sure more than 42% of people that have a cell phone own a smartphone, but I don't know, maybe that's just my bias. Determine to the nearest percent the probability that any Canadians you met in the month during which you did the survey would have a smartphone. So again, there are multiple different ways that we can approach this. I think that the most, I guess, like classic way of doing this would be to draw a tree diagram. Okay, so I'm going to go ahead and draw that. And we're going to say cell phone, and then no cell phone. Okay, so 91% of Canadians own a cell phone, which means that the other 9% do not own a cell phone. And we can already say logically that if you don't own a cell phone, then you definitely don't own a smartphone because you don't have a cell phone. Okay, so we don't have to worry about this branch here on the bottom because it's not going to change our probability in any way. But now from these 91%, 42% own a smartphone, which means that 58% do not own a smartphone. So again, I'm going to kind of shorthand this. I'll use SP for smartphone and then no SP for not having a smartphone. So the probability that a Canadian would have a smartphone, again, we're just looking at this particular branch here because this is the only branch that gives us the amount of people that have a smartphone. So this is 91% times 42%, or 0.91 times 0.42. I'm going to go ahead and use a calculator for this because I did not do this calculation ahead of time. So 0.91 times 0.42 gives me 0.3822. If we change that to a percentage, again, just multiply by 100 to change to a percentage, is 38.22%. But it says round it to the nearest percent, so we're going to go ahead and just round this to 38%. All right, so again, a very straightforward question. Example 4 says, Hillary is the coach of a junior ultimate team. Based on the team's record, it has a 60% chance of winning on calm days and a 70% chance of winning on windy days. Tomorrow, there is a 40% chance of high wind. There are no ties in ultimate. What is the probability that Hillary's team will win tomorrow? Now, one thing that I want to point out that we haven't really talked about yet is how do we make the branches on our tree diagram? Because again, I find that tree diagrams are the most efficient way of like demonstrating these kinds of probabilities, including in the next lesson that we're going to see. And so when we read the question, we say that there are two different probabilities for winning. So because there are two probabilities for winning, depending on what kind of day it is, that's going to be my second branch. Okay, because then we get a branch that branches off of the first one, and we get a branch that branches off of the second one as well. So because we have two probabilities here of winning a game, those are going to be our second branches that we're going to make in our diagram, which means that this other percentage here, this is going to be my first branch. Okay, so my first branch is either going to be windy or calm. Okay, the percent of it being windy is 40%, which means that the percent of the calm is going to be 60%. It's going to make up the other part to make up 100%. And then from there, we're going to branch off. So we have a 70% chance of winning on windy days. So win and lose. So on a windy day, we have a 70% chance of winning, which means a 30% chance of losing. On calm days, we have a 60% chance of winning, which means we have a 40% chance of losing. Okay, so this is how we're going to draw our tree diagram. And then it says there are no ties, so we don't have to worry about that. So the question is, what is the probability that Hillary's team will win tomorrow? So what we want to do is we want to follow the branches that lead to us winning. So if we go up the top branch, then we have that probability of winning. And if we go down the bottom branch, we have that probability of winning. So we're going to calculate those two probabilities separately and then add our totals together at the end. Okay, so the probability of it being windy and we're winning is equal to the probability of it being windy times the probability of winning given that it is a windy day. So we're going to multiply these two percentages together, you get 0.28. If we follow the second branch, the probability of calm and winning is equal to the probability of it being calm times the probability of winning given that it is a calm day. So both of these are 60%, so that's 0.60 or 0.6 that we're multiplying 2 times, and we get 0.36. So the probability of winning is equal to the probability of windy and winning plus the probability of calm and winning. And again, I don't know how picky they are in exams when it comes to this kind of notation, but this is how you would write it. So when you add these up together, you get 0.64, which if you change it to a percentage is a 64% chance of winning. So again, sometimes we use the formula, sometimes we don't necessarily write down the formula, but just kind of thinking about like different pathways and different events happening and just trying to follow the correct paths to get the correct answer. That's kind of the whole idea behind this H3 part of the course.